Okay, this is for Jerry and Tom. I've been slowly corresponding with Jerry on getting a undergraduate level paper together. And I think the last one that we were sort of contemplating was using integration by parts, maybe upgrading existing papers, definitely tried and published kind of idea there. So maybe I have something a little bit to add to previous things. Not a lot. It's not a earth-shattering idea. What probably is more earth-shattering, and still at an undergraduate kind of level, is to upgrade what I'm calling Hermite. That's the French pronunciation of hermit. Is what I'm calling a function. So I'll get into that in a moment. This is a overview of what I'm thinking I'll do with this video. Okay, so that would be not totally earth-shattering, but it would be, something that is a shortcut to irrationality and transcendence proofs of E and pi. A shortcut, a better, quicker proof, which that's more original, and it's I think it's pretty easy and pretty obvious, with these Leibniz tables that I've been spewing out of my mouth and computers for countless years. It's an application of that. It's pretty fast. I think Jerry could get it. I think Tom could get it with a yawn, and I can get it after 5 years of fiddling with it. The other one is a earth-shattering thing, genuine earth-shattering, pretty earth-shattering. That's Goldbach's conjecture. Goldbach claimed that every even number, if I get this right, every even number is the sum of two primes. And just to show you, in fast and brief, let me review that a little bit further. So Goldbach's conjecture, I think, was made 1700, 1800, something like that. It's very, very simple to state. I mean, it's one of these number theory things. Any even number is the sum of two primes. So let's take an even number like 14, 7 plus 7. You're allowed to repeat, and there's also 11 plus 3. And it is blisteringly easy to state and find up-teen examples. You take an even number and somewhere along the line, you'll get two primes. And to prove that, though, is a Herculean effort. And I think I had some stuff that, some people, read at Vixra. I think I got 200 hits on, one of them and 100 and some on the other. I can claim to have proved it. The conjecture is correct. Every even number is the sum of two primes. So I had some interesting ideas, but I don't think either paper does what I claim and a proof that everybody accepts. The second paper, the one less traveled, read by mathematicians out there, I think is a proof. It's a weird induction proof. But I don't think it's acceptable. It's not two meat and potatoes. Now, here's the thing for, Tom and maybe Jerry. It's not particularly complicated. It's a little complicated. As you might imagine, if you're going to prove a centuries, decades for sure, old open number theory problem, it might get a little complicated. So here is where I am with that. And then in a separate video, I'll get on with the Leibniz tables, prove something that expedites makes proofs of irrationality and transcendence faster. So here's the idea. I said to Tom that there's stuff not in the Vigstra articles that I'd like to explore. I feel I'm, I don't know, guilty of not getting this out, even though it might not work. It's something that's, pretty damn interesting. This is more or less the paper I have published. At some point, this was, I think, my contribution. As far as I know, this is unique. You give it an even number. You can always write it in 2 rows. That is, you can, count up to that number using 1 through 10. Then you go up to the second row and 10 through 20. And then you do the sieve thing. After the first occurrence of a multiple of a number, you cross it out. So, 2 is left, 4 goes, 6 goes, 8 goes, 10 goes, 12, blah, blah, blah. 3 stays, and then 6, da, 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 da. And then you're left with columns that always add to the number. As it stands, this is a kind of a combination of something Gauss did in determining the sum of 1 through 100. You might remember that proof. You split them up, you add them, and you get the same thing divided by 2. So it's also a sieve of Eratosthenes, where you get all the primes by doing this thing. So you do it kind of doubled up there, and sure enough, you get, I think, all of the primes that'll add to 20 using this. So that was pretty interesting, and it's a nice, way to have an activity for, grade school or something like that. Theory of the sieve, I gave a little bit more of an idea here, which is a little bit complicated. It's not that complicated. You split up 44 into all its primes and all the remainders of its primes, as well as multiples of primes. So 44, let's see if I can do this, is, can I do this? 13 times 5 plus 3, something like that. I'm going to try an easier one here. 2 times 22, in other words, 3 times 14. 3 times 14 is 42 with a remainder of 2. So it's 5 times 8. Let's see if you can see that there. 5 times 8 is 40 with the remainder of 4. So the remainder is the larger number. See if I can do this one. 17 times 2 is 34, plus 10 is 44. Where's the one I was trying to do here? 13 is a prime, times 3 is 39, plus 5 is 44. You do that for all the primes, and then you make a kind of inference from that. And at some point, you get linear functions involved with making sets. All right, so linear functions sets, and then over here you give all the prime factorizations, and eventually you get these things with no prime factorization for either number. So 44 would be the sum of 37 and 7, 31 and 13. So it gives kind of a theory for that. Now the thing to remember is linear functions. And now here's the new stuff that has not been, written up. Inverse linear functions. You do inverse linear functions, and then you start to get some patterns which have a symmetry, which I think Erdős, I think it's how you pronounce his name. Everybody has an Erdős number. Some people have an Erdős number. And, with that, he said, Erdős did, that symmetry is the root of good mathematics. And you fiddle around with these inverse functions, and eventually you get things like this, where you can predict that there will be a solution based on a symmetrical pattern. So this one I will, for posterity's sake, maybe somebody will follow this at some point. At some point, these are inverses of 2. The inverse of a linear function, this is where it's pretty simple, is a linear function. And you do that in here for these numbers, and you get remainders, and eventually the remainders become symmetric. And that implies that you have a solution. And if this was proven, you see a kind of, at least I see a kind of algebraic structure there, a kind of symmetry of group theory, rings, all the stuff hopefully Tom is up on. You see that symmetry there, and maybe, it's not like I've proven this, but maybe that symmetry is suggestive, and somebody with a good abstract algebra kind of mind could see it and give a proof. So that's in a very quick nutshell what that one is about. Okay, and there's more there. I haven't filled in all the blanks, obviously, where these inverse and regular linear functions come from. So we'll call that a wrap. I will next attempt to warm us up. See if either of you can do anything. Except nod your head and play like you're interested. So if you can say I get it, I don't get it, and you made a mistake, something like that, that would indicate that I really have some partners in crime here. Otherwise, it's okay, if you just want to smoke cigarettes and cigars and fly your planes and eat your Swedish meatballs and drink your wine. That's fine too. Just pretend for Jones to amuse him because he asks you to. But if you really are into doing this, which I don't know how you would do if you're working, teaching 4 classes, 5. Jerry does 20 classes in 3 different locations per week. So does he have time to fiddle with Goldbach's conjecture or Leibniz according to Jones? Question mark. When you're both retired, if you're still, cognizant, maybe this gets more interesting. So we'll leave it at that. I'll do at least one more video, maybe a second on Goldbach. Okay, we'll see if anybody watches this.